So next, we will optimize lambda offset and row offset for binary erasure channels. We will show how we can achieve this goal using exit chart analysis. So the main question we ask ourselves is that given some constraints, and usually we are given the design rate, potentially we are also given the maximum variable node degree and the maximum check node degree, what is the best possible lambda offset and best possible row offset? The end of last video, we have seen that we can try to do this analytically, and we saw that this leads possibly to a code of rate 0, so we'll not do that. And what we'll present now is a practical approach to construct good lambda offset and good row offset. So how does this approach work? Well, we start with the threshold condition or fixed point condition. So we have the case that we have a threshold of at least epsilon star if epsilon star times lambda of 1 minus rho of 1 minus xi is smaller or equal than 0 for any xi between 0 and 1. Now this is a continuous problem, so we have a continuous function. So we would need to check this for infinitely many x's. But we know that this function is usually well behaved. It's a polynomial, so it doesn't change crazily. So what we can do is we can discretize and just look at discrete steps and hope we don't miss a point where it's not 0 between 2 points. So what we do is we discretize xi, and we discretize xi with d steps. So we set xi tilde I is equal to I divided by d, and we let I run from 1 to capital D. So we go from 1 over d, 2 over d, 3 over d, up to 1, which is d over d. So we can transform this fixed point evaluation from a discrete problem, from a continuous problem, into a discrete problem. And we just need to be careful that we select d sufficiently fine in order to miss no fast changes of this function. So a good choice is some d between, say, 100 and 5,000. And we saw that also many of these changes, they happen for small d, so it can also be beneficial to use a logarithmic discretization scale, for instance, but we are happy with a linear scale. So first thing we do is we fix row offset. So we assume that row offset is already there. We have some genie that gives us row offset, and then we say we want, for this given row offset, we want to find the best possible lambda offset. Okay. So we have this fixed point condition of epsilon and lambda. So this is epsilon of lambda of 1 minus rho, 1 minus xi. We need to know this is larger equal than 0. And we now insert lambda, or the evaluation of lambda. So this is epsilon times the sum over lambda I times 1 minus rho of 1 minus xi to the power I minus 1 minus xi. So this, for a given xi, is given. And this is a function that is linear in lambda. Linear in lambda, this is the factor that is given. We are not interested in this. We want to optimize lambda. And this is a function that is linear in lambda. So that's good. And this means that we may use the framework of linear programming. Recall when we optimized the capacity, we used convex optimization. And here we hope that everything is linear, so we may use linear optimization, which is a special case of convex optimization that is much simpler. So how do we proceed then? So this is what we have already. So now, what do we want to optimize? So we want to maximize the rate of the code. We want to find a code that converges for a specific row of Z. It converges, so it should be able to converge, but it should have the highest possible rate, because that means we can put the most amount of information into our code word. The rate is maximum. We don't want a code with a very low rate. We want a code that has the highest possible rate for a given condition. So usually we would like to maximize the rate. And now let's see how we can do this. So we start by the definition of the rate, and the rate can be expressed in terms of the degree distributions. Rho is given, so the numerator, that's a constant. That is something that we know. And if we look at this integral in the denominator, this integral is nothing else as the sum over lambda I divided by I. We insert lambda tau, we integrate, we have lambda I times z to the power I minus 1, which is integrated is lambda I times z to the power I divided by I. We insert 1 for z, that gives us the sum over lambda I. So if you don't believe me, we can just quickly do it. Integral from 0 to 1 of lambda tau d tau is equal to the integral from over the sum of lambda I times z to the power I minus 1 between 0 and 1 and dz. So this is same as the sum over lambda I times z to the power I divided by I, where we insert 0 and 1. So this is equal to the sum of lambda I divided by I. Okay, so we have this polynomial, and when we would like to maximize the rate, this means we should maximize the denominator, because we have a minus sign over here. So usually maximizing the denominator will minimize this term. So as we have a minus sign, it will maximize the rate. So maximizing the rate, RD, corresponds to maximizing the expression lambda I divided by I, which again is a linear function in I. Lambda I multiplied by a constant, which happens to be 1 over I. So we have everything we have now, so we can formulate an optimization problem. And in this case, it's a so-called linear program to find the values of lambda. So the program we have is on this slide. It's over here. It looks a little bit complicated, but we are going step by step. So the first thing we have is we would like to maximize the sum over lambda I divided by I. This is what we had. So lambda I divided by I, subject to. So we have some constraints. We cannot freely choose the lambdas, otherwise we should just choose lambda is infinity. Lambda is infinity, this will definitely maximize this sum. So we need to have some constraints. First constraint is that the lambda i's, they must be larger or equal than 0. If they are fractions, they cannot become negative. Then the sum of the lambda i's must be equal to 1. Again, they are fractions. The sum of all the fractions must be equal to the total, which is 1. Then we have the fixed point condition. So now we discretize Xi. So recall that Cj tilde is equal to j divided by d. And we have this fixed point condition that we insert. So the sum over lambda i's times epsilon times 1 minus rho 1 minus Cj tilde power I minus 1 minus Cj tilde must be smaller or equal than 0 for every j between 1 and d. So this means that we have convergence to 0 is possible. And then we add the so-called stability condition that we have derived in the previous video, which gives us a constraint on the number of degree 2 nodes or edges connected to degree 2 nodes. So lambda 2 should be smaller or equal than epsilon divided by rho prime of 1. And this is a pretty standard optimization problem, and you have a ton of tools with which you can optimize those. For instance, you can use GLPK, which is included in Octave or in MATLAB. You have linproc. What you can do is linproc in MATLAB. If you're using Python, you can of course use CVXPy, because a linear program is also a convex program. So you can use CVXPy in Python. You can use CVX in MATLAB. Or you can use pulp in Python. And many more. So when you do this, we can solve this program, and we can find, for a given row offset, we can find the best possible lambda offset. So now how do we find row offset? Well, we fix row offset by looking at something that is called a concentrated check node degree distribution. So first, we say we fix an average check node degree DC average, and then we have a row offset that contains two different degrees. We define DC tilde is the floor of DC average. It's the integer part of DC average. So we cut off everything coming behind the comma. It's the floor of DC average, so that's DC tilde. And we assume that we have variable nodes, we have check nodes of both degree DC tilde and DC tilde plus 1. So they are concentrated around DC average. We have some non-integer DC average. We have DC tilde, a little bit smaller, and we have DC tilde plus 1, just a little bit after. And we get the following row offset. So row offset essentially is a degree distribution such that you get 2 DC average. So how do we see this? Well, we can quickly show that for this given row, that's exactly the case. So let me quickly just take a copy of this expression so that we have it at our disposal on the other slide when we derive it. So we put that guy up here, and then we can start taking a closer look at the expression. So we can calculate DC average, but I will start with calculating 1 over DC average, because that's going to be a little bit simpler. So this is equal to the integral from 0 to 1 of rho of tau d tau. Well, now we just insert this bad boy into our equation, and we carry out the integration. So first we have this constant, and so we have DC tilde times DC tilde plus 1 minus DC average divided by DC average. Now we need to integrate z to the power DC tilde minus 1. That's equal to tau to the power DC tilde divided by DC tilde. Then we have the second term. Second term here is DC average minus DC tilde times DC tilde plus 1 minus DC average divided by DC average. Now we integrate, that is tau to the power DC tilde plus 1 divided by DC tilde plus 1. And we evaluate this guy for 0 and 1. So let's simplify where we can simplify. So we can cross out DC tilde. And that seems to be about it. And of course, if we insert a 1 here, we need to replace tau by 1. So this is going to be equal to 1. And this is going to be equal to 1. If we insert 0, both terms will vanish. So we can go ahead and we can put the two terms on a common denominator, which would be equal to DC average times DC tilde plus 1. That's the common denominator. So then we have the left fraction that's going to be DC tilde plus 1 minus DC average times common denominator DC tilde plus 1. And then we have the second part, that's plus DC average minus DC tilde times DC tilde plus 1 minus DC average. Okay, so now we can factor out this guy. So that's a common factor of the first and the last summed. So we're going to just factor this. So DC average times DC tilde plus 1 is in the denominator. And now we take out this factor. So it's DC tilde plus 1 minus DC average times. We have a DC tilde plus 1, this guy, minus DC tilde, minus DC tilde. Okay, that's very nice because this DC tilde cancels. And then we have plus DC average. Must not forget this term over here. Okay, so what are we left with? We are getting close. It's simplifying. First, the denominator is DC average times DC tilde plus 1. Then we have the first parenthesis, so it's DC tilde plus 1 minus DC average plus DC average. Okay, very nice. So this guy cancels. So we are left with DC tilde plus 1 divided by DC average, DC tilde plus 1, and again we see DC tilde plus 1 cancels, and indeed we have 1 over DC average. So we have shown that the expression from the previous slide indeed, or this rho of z indeed leads to an average check-not degree of DC average. So perfect. So we have done that. So we have this slightly complicated looking rho of z. And now we can use that one. So if we look at the design rate, we don't need to calculate this integral. This integral, the integral from 0 to tau 1 of rho of tau d tau, recall what we just derived, it's exactly this guy. So that's exactly 1 over DC average. We don't need to have this integral. So we can just replace this by 1 over DC average. So the design rate actually is 1 minus 1 over DC average divided also by the sum over lambda I divided by I. Okay. So now instead of specifying rho of z, we specify DC average. For each DC average, we calculate rho of z. So now, how does the optimization work? We use binary search, essentially. So we use an iterative procedure, and we'll show how it works with an example, because that illustrates quite well how you can do the optimization. So we would like to design a code that has a target rate of 0.7. And then we need to fix some parameter. So for instance, dV max is equal to 16. And we sweep DC average between 3 and 22. Then we fix a threshold that we call T delta, and T delta is a small enough number. And now we use a binary search to find a code that is close as possible to the target rate. Remember, we want to maximize the rate. So in our procedure, we maximize the rate, and then we change epsilon until we find a maximum rate that is close to the target rate. And what we do is the following. So we start just in the middle. So we start with epsilon equals 0.5. And we set delta epsilon to be equal to 0.5. So we start with the epsilon in the middle. And now we sweep DC average. Sweep through DC average and run the optimization for every DC average. Of course, we do this in discrete steps. And then we pick the DC average that leads to the largest rate. So we select the DC average leading to the largest rate. So we carry out the optimization for every DC average. We pick the DC average that leads to the largest rate. And if this rate is larger than the target rate, means then we can put more information into our code rate. But it doesn't correspond to the target rate. It's larger than the target rate. It means we can increase epsilon because our channel is too good. We can actually work with a worse channel where we can put more erasures and then get a slightly smaller rate. So then we set epsilon equals to epsilon plus delta epsilon divided by 2. And if the rate that we get, RT max, is smaller or equal than the target rate, then we set epsilon minus delta epsilon divided by 2. And then we check if delta epsilon is larger than our T delta. If that's the case, then we halve delta epsilon. So then we just set delta epsilon divided by 2. And we repeat until our delta epsilon, which is our search space, gets so small that we found our code. And finally, we pick the best DC average and the lambda i's corresponding to this DC average. Of course, we provide a Jupyter notebook where this is implemented. We had started with pulp. Unfortunately, pulp changed its interface, so we need to work it a little bit. So it doesn't work at the moment, but we'll get it to work. Or possibly we're going to move to CVXPy because we have already used CVXPy for the optimization of the capacity. So we can as well reuse CVXPy over here. So let's take a look at the example. So we start at iteration 1 with epsilon equals 0.5 and delta epsilon equals 0.5. Then we run the optimization for DC average starting at 3 up to 20. And we see that we get codes of a certain rate given by this curve. Eventually, it will stop. And if DC average becomes too large, it means we cannot find a suitable code anymore. There is no way that the selection of a DC average leads to a lambda offset that leads to a code that can actually decode, that is decodable, that can converge. Now we look at this curve and we pick the largest point of this curve with the highest rate. That's marked here by the dot, and that leads to a rate of almost 0.5. So this rate is smaller than the target rate, which means our channel is too bad, means we need a very small rate. Our target rate was 0.7, but we cannot fit that into our code. Our rate is too bad, so we need to have a better channel. So we need to decrease epsilon. So what we do is we just set epsilon is now epsilon minus delta epsilon divided by 2, which is 0.25. And delta epsilon becomes anyways delta epsilon divided by 2 being equal to 0.25. Okay, so that brings us to the second step. So now epsilon is equal to 0.25. Delta epsilon is also equal to 0.25. Now we run the optimization, and we see that now for a wide range of DC average, we can find good codes. Now we find the maximum is obtained here for a DC average of 15.5 something. We have a maximum rate of 0.7444, and that's larger than our target rate. So this means now our channel is too good. We can fit a very high rate code into it, so we need to worsen our channel a little bit. So what we do is we set epsilon equal to epsilon plus delta epsilon divided by 2. So it means we can afford more erasures, and this is equal to 0.375. And again, delta epsilon becomes 0.125. Okay, on to the next try. So we start with epsilon equals 0.35, delta epsilon equals 1/8. We run the optimization and we get this curve with an RD max of 0.618, which is below our targets. So now it means again our channel is too bad. We need to improve the channel. So delta epsilon is equal to 0.375. The channel is too bad. We need to improve it. So we need to reduce the number of erasures minus delta epsilon divided by 2. So now this gets a little bit out of hand. So this is 0.375 minus 0.375 minus 0.0625, which is equal to 0.3125. 0.3125. And delta epsilon gets smaller again, delta epsilon becomes 0.0625. Okay, so we are here. Now we had epsilon equals 0.3125 and delta epsilon equals 0.0625. We run the optimization. We find an RD max that is smaller than the target rate. So again, our channel is too bad. We need to improve it a little bit. So it means we need to further decrease epsilon. Now it's not something that I can easily do in my head anymore. So we decrease epsilon a little bit. So we go to 0.28125. Now we find a code that is slightly larger than our target rate. But you can see that we are homing in on the target rate very, very well already. We're just wiggling a little bit around the target rate. So now it's larger. It means our channel is too good. So we need to decrease it or increase epsilon a little bit, make it a little bit worse. So we have an epsilon of 0.296875. Now we're a little bit below. So we need to decrease again. And we finally zero in on the maximum rate. So eventually we get very close after 8 iterations, 9 iterations. And here we are after 9 iterations. So we are fairly close. We have a slightly smaller rate, but rounding it almost leads to 0.7. And our delta epsilon, of course, is also, we stopped at 0.001, but we could make delta epsilon even smaller than coming. So if you didn't get this, take a look at the source code that we provide, and there you can follow all the steps and you'll see how it's being done and how the, what is actually being done in the background. You can play around with the parameters. You can design your own codes as well. Okay, so here's the exit chart of the code, and we see that the curves match pretty well. I actually zoomed in, so I don't start here at 0. We start here at 0.7, because otherwise you won't see too much, but we see that we have a very well matched exit curve. And of course, we need a lot of iterations, but the code has a pretty nice threshold. So here are here's the final result. So our lambda of z is given by this. So lambda of z is 0.28243 times z plus 0.14235 times z squared, and so on. So we have a maximum degree of 16. That's what we get over here. The average check note degree, DC average, is equal to 12.98, so almost 13. That's also something we see. And the code has a threshold of 0.2949219, which is very close to the capacity of the binary erasure channel, which is equal to 0.3. And if you want a better threshold, if you're not happy with this threshold, what you need to do is you need to increase dV max and DC max. Of course, you could allow also more freedom on rho of z. We have some constraint because we have this check average. But it turns out that for most codes in the practice, this is actually sufficient if we put just an average check note degree and be very close to this average check note degree. So again, you can take a look at the Python notebook that is provided with the code, and there you can see how to do the distribution optimization. So here's another distribution, another code that really pushes this to the limits. So this is one that has been specifically optimized for the binary input AWGN channel. But you just to give you an idea of what degree distribution they used like. So they have a maximum variable note degree of 8,000. So that's pretty large. They have a DC average of 18.5. Again, concentrated on the check note. So it's the same idea that we just had. DC average, and then you have some with 18, some with 19. Design rate is equal to 1/2. And this is the lambda offset. This has a threshold within 0.0045 dB of the capacity, but it's a code that you will never encounter in a practical setting because the variable note degree is just too large. But it's just to show how close to capacity you can get if you really push it. But you need a high average variable note degree. That's the drawback of this thing. So to summarize, on the erasure channel, we have irregular LDPC codes, and LDPC codes are very powerful channels. We have very simple analysis on the erasure channel that allows us to understand and design codes that have a threshold that's very, very close to the limits. The threshold can be attained if the length n becomes asymptotically large, and if we can invest an infinite number of iterations. That's a take-home message. And if you want to have a code that converges well enough for a fixed number of iterations, you need to put some effort. That's actually a topic of active research. So now we have finished the analysis on the binary erasure channel. Now we are ready to move on to other channels. And the binary erasure channel already gives us a very, very good insight of what is going on and what we can do on other more general channels. So with this, we are done for the erasure channel. And in the next video, we're going to look at more general channels.